Okay, so Muriel Livernet has kindly agreed to speak today on a homotopy theory of multicomplexes. So take it away.
Thank you. Good morning, everybody. So I just tried to share my screen. Should work normally. Okay, so thank you very much for giving me the opportunity to talk in this seminar. This is my first, so I hope that you will be all indulgent. And don't hesitate to interrupt. If you need more explanation, if my writing is bad, if you don't see anything, or if you don't hear me. So I'm going to talk about homotopy theories of multicomplexes. This is joint work with, so there are mainly two papers, one with Joanna Cirisi, Daniela Santander, and Sarah Whitehouse. And the second one with Shinfu Egan and Sarah Whitehouse. So I will split my talk into 4 parts. Well, the first part is what are multicomplexes. I think I will start by defining them and then explain you where you can encounter them. And indeed, I'm pretty sure that you have already encountered them somewhere. Multicomplexes give rise to filtered complexes and then to spectral sequences. And then you can ask whether two multicomplexes are weakly equivalent if they are quasi-isomorphic at a certain page of the spectral sequence. I will explain a little bit in some cases where it arises. And so the aim of this talk is to present model category structures that encapsulate this notion of weak equivalence, which is not the usual notion for complexes or even bicomplexes, for instance. So in the paper with Joanna and Daniela and Sarah, we proved model category structure for filtered complexes and bicomplexes. And in the paper with Shinfu and Egan, we just give the full model category structure for any multicomplexes. Multicomplexes, there are special cases. I mean, you can truncate the multicomplex. I will explain in the first part. And example of multicomplex are bicomplexes, but there are some others. So the notion of n multicomplex will be explained in the first part. But we prove also that there are model category structure for any n and any r. R is a stage of the spectral sequence you are looking at. So the third part of the talk will be really short and explain you that we can compare some of the model category structures that I will explain. The fourth part is a work in progress. Mainly we are looking for, I mean, the model category structure that I will explain is a model category structure where all objects are cofibrant. So we are more interested in explaining what are cofibrant objects. And well, work in progress is what kind of tool do we have to try to understand or to explain what are cofibrant objects in the model category structure. So is that clear, the plan of the talk and what I will talk about for everybody? So now this is a writing part, right? So does it work like this? Yes. So first part, what are multicomplexes? So I'm working on a ground ring. This is, I mean, normal ring commutative with unit. And I'm looking at modules over this ring, but I mostly look at bi-graded modules over this ring. So Mij will be like an R module, and a bi-graded module is a collection of Mij, and I'm taking Ij in Z. I mean, so it's really in the unbounded cases that we are working. So a multi-complex is our bigraded module together with a collection of maps, di, of by degree minus I, 1 minus I, such that there's a sum which is 0. And I here is greater than 0. So I have a d0 of pi degree 0, 1, a d1 of pi degree minus 1, 0, and so on. So for instance, if L equals 0, you get that d0 square equals 0. So a multi-complex starts with a complex. I mean, it just think about a columns, a bunch of columns of complex of pi degree 0, 1. So it's cochain complex. But when you go further, L equals 1 gives you that you have a d1 of pi degree minus 1, 0. So maybe just to check, d0 is this direction, d1 is that direction, and they are commuting. But now look at what happens in L equals 2. You have this equation. So you have a d2, and d2 goes 2 on the left and 1 down. So unless d2 equals 0, you don't have a bicomplex as usual. I mean, you don't have d1 square is 0. Okay. But of course, if all the di's are 0 up to a certain degree, you can look at this category also. But by category, I need to specify what are morphism. So the morphism I'm looking at here, I just morphism of pi degree 0, 0, which commute with every di's. So there's this category of multi-complex, and we'll have this category of n multi-complex. So by saying that these are multi-complexes such that the I is 0 for I greater than 1. Than n. So for instance, one multi-complex are just these bigraded modules where you have a d0 of pi degree 0, 1. So it's kind of collection of cochain complexes. So we called it vertical bicomplex in previous paper, because this category plays an important role in what I will say later. Two multi-complex are bicomplexes, are called also double complexes. And by the way, multi-complexes are called in some papers also twisted complexes. So just a D0 and just a D1. And three multi-complex, you have D0, D1, D2, and so on, okay? And when n, so sometimes, I mean, just for the statement of theorem, we sometimes write n equals infinity, and infinity multi-complex means just multi-complex, that's all. I mean, just a terminology helping. So before starting all the story and the technical details, I want to show you where this kind of stuff arose. So I have to. So where can you find multi-complexes. So, but before that, because I mean, this is where it was used. When you have a multi-complex M, you can define the total complex. So, I mean, I'm cheating a little bit with this product, but I don't want to enter in these details. So where do I cheat? I need to do something. Sorry. Okay. So, I mean, this is a mix of product and co-product here, but I don't want to enter it just so that D is defined. And D is sum with signs depending on the N and the A you are looking element. I mean, where are the elements in M? But the thing is that when you do that, you have that D square is 0. I mean, the relation that I define for a multi-complex gives you complex D square, and it has degree 1. Okay. And then this is filtered by the column filtration. So the filtration is increasing. And this yields a spectral sequence. And we write ERM for the R stage of the spectral sequence. And we say that F from 2 multi-complex is an ER equivalence if ERF is a quasi-isomorphism.
Hey, Muriel, this
Yes.
is David Ayala. I have a quick question.
Yes.
So am I right that the ER of M also depends on the parameter N? If I'm
yeah, so in some sense you will have, and I will specify it. So you have, it's more than the parameter N, it's because it's bigraded, you have a bigrading. Is it the question? And you have, I mean, a map of by degree minus R, 1 minus R, that squares to 0.
Okay, great, thanks. I see.
And so the homology of this complex, it's called an R complex because it's not like a complex of degree minus 1, just R complex because it has this by degree. The homology of this is precisely ER plus 1 as a R plus 1 stage of the spectral sequence.
Muriel, the thing on the right is an N, correct? ER of N.
No.
FR going to ER of...
Here, you mean here?
Yes.
No, sorry. So this is how you define the spectral sequence of multi-complex M.
Oh, it's the differential. I thought that was an F. I'm sorry.
No, I'm sorry. Maybe.
No. Yeah.
Yeah, this is the differential in the spectral sequence. So when you have a multi-complex, remember that you have all these D0, D1, D2, and DR as precisely the by degree, the same as delta R. Okay? The thing is that delta R is not DR. I mean, it's much more than that. It's a combination of all the DIs, D0, D1, up to DR. So this we gave a formula with Stefanie Ziegenhagen and Sarah Whitehouse, an explicit formula computing this delta R. I will come back to this later, not to the formula, but I just needed this to explain you what are the examples. So examples, okay. So there is the original one of Val in 61. So he was interested in trying to find a free resolution of a group. So KGH are groups. This is an extension of groups. And computing a free resolution of G whenever you have a free resolution of K and of H. So using this, he obtained a spectral sequence. And this spectral sequence came from a multi-complex. So finding a free resolution of G free resolution of K and H gave a spectral sequence, or maybe gave a multi-complex. So for example, there is an example that is explicitly treated in this paper where K is D mod R. I mean, it's a cyclic group of order R. H is a cyclic group of order S. And he built a multi-complex, which is a free multi-complex. So you have only D0, D1, and D2. And this gave a free resolution of G by just using a spectral sequence associated to this multi-complex. So this is one, example, the original one. Now, if you are interested in structure up to homotopy, like A infinity structure, E infinity structure in the context of, let's say, homotopy transfer theorem with formulas, I would say. If you start with just a vertical bicomplex, like the one with D0, and you want to transfer this structure up to homotopy, you end up with a multi-complex. In some sense, there's a opera theory that tells you exactly that this is a minimal resolution of the dual numbers, of the operad of dual numbers. If you start with an A infinity algebra and you have, spectral sequence, you want to understand what are the multiplicative structure that are in the spectral sequence. So this is some work of Lapin and maybe Lapin and Erskovich that gave multiplicative structure on spectral sequence. On spectral sequence. And this involves multi-complexes. Sagav tried to, studied homotopy theory of differential graded algebras, but over a ring. And he proves that the notion of A infinity algebras is not enough, to build some minimal models. And came with the notion of what is calling derived A infinity algebra, which is not derived in the sense of, most of people might understand it here, but this is a combination of A infinity structure and multi-complex structure on a given object. And indeed, he came with minimal models for differential graded algebras. but these minimal models are not E0 equivalents, but E1 equivalents. So that's where our project with Sarah Whitehouse started, all the understanding of this ER equivalence with multi-complexes. I mean, the idea is just to understand ER equivalence or quasi-isomorphism. It's the terminology that I used for the right infinity algebra. So that's the whole target of our work with Sarah Whitehouse. Another example.
I have another question.
Yes.
So in that first example of wall, could maybe I missed it, or if you could say what the bigraded module is.
So I have the example just right to me. May I postpone it to the end?
Okay,
of the
that's
talk?
fine. Yeah, it sounds good.
So, the last example that I want to highlight is a recent work of Joanna Ciresi and Wilson in differential geometry, where they build Dolbeault cohomology for almost complex manifold, and built this cohomology and wanted the spectral sequence, like the Fröhlicher spectral sequence for complex manifold. And they built it using kind of different filtration, but this filtration came from a multi-complex, which is a 4 multi-complex. So a 4 multi-complex, I say, is at the basis of Dolbeault cohomology for almost complex manifold. And to be honest, I can tell you more about that, but I'm pretty sure that Joanna will be happy to answer questions concerning this paper. So I hope that I gave enough example coming from different settings, just to motivate the fact that multi-complexes are really important. I mean, as chain complexes, but sometimes you don't have chain complexes, but you have chain complexes up to homotopy, and this is the notion of multi-complex. So now I will go to the model category structure story. So maybe I state the theorem and then I comment it. So again, we proved it with Joanna Ciresi and Daniela Egas-Santander and Sarah Whitehouse for the case of bicomplexes, and we extended it with Shin-Fu and Eigan for the case of n multi-complexes. So there are 2 parameters in this theorem. N is n multi-complexes. So it can be bicomplexes, it can be 3 multi-complex, 4 multi-complex, or n can be infinity and it can be multi-complexes. And R is a second parameter, and it will be the notion of ER quasi-isomorphism. So you have your spectral sequence associated to a multi-complex or n multi-complex. and you are looking at the R stage of the spectral sequence, and you ask whether it's a quasi-isomorphism. I mean, the morphism you are looking at. So there is a coherently generated model category structure on n multi-complexes with, so I just give you the weak equivalents. These are ER quasi-isomorphism and vibration. And I put an R here just to remember that we are at the R stage of the spectral sequence. These are map of multi-complexes or n multi-complexes such that EI of F is by degree wise surjective for all. Okay, so and of course cofibration will be the ones that are the left lifting property with respect to a cyclic vibration. Okay, so I would like to show you an idea of the proof of this theorem. But maybe just before that, if I'm defining E0, so these are the class of ER quasi-isomorphism, meaning that weak equivalence is ER here. So E0, if, I don't know if you remember, but maybe the filtration of a multi-complex. Oh, sorry. So I have defined this, but if you get back, I guess this is, okay. And the differential delta 0 is precisely D0. So E0, it's just quasi-isomorphism of multi-complex with respect to D0. So we have chosen, to start from D0, and then we have chosen the column filtration on purpose because we are dealing with multi-complexes. So with multi-complexes, D1 square is not necessarily 0. Of course, if we start with bicomplexes, we could have also started with a row filtration and started with D1. So, which might give you another model category structure for bicomplexes, okay? So it's quite clear that this is a nested sequence of a class of maps, because if you are a quasi-isomorphism at level stage 0 of the spectral sequence, and you are an isomorphism at stage 1, and then isomorphism at stage upper than 1, greater than 1. So this gives you localization of homotopy category, and I will write. This is homotopy category with respect to E0 equivalence. Okay. So the thing is that it's not localization at the level of the Quillen model structure. I mean, there's no hope, some sense that the identity between these is a localization. Okay, so do you have any question?
I have a question.
Yes.
This is Chris Negron. This is a silly question. If we go back to this infinity example, so those were, you need to consider n complexes for arbitrary n in order to have these kind of minimal models over an arbitrary ring.
Sorry. So this was here, yes. Can you repeat the question?
Yeah, so I'm just asking about, so for example one, you just have bicomplexes, right? Basically.
No, I said, so the free, I said a free multi-complex.
That's 3, okay.
Yeah, and here this is just multi-complexes. In example 2 and example 3, it's a 4 multi-complex. So we are above. I mean, there's all the story of bicomplexes.
So the A infinity one is a 4 multi-complex, is that?
A infinity one is in the middle.
Yeah.
And this is multi-complex. I mean, really multi-complexes. I mean, n is infinite.
Okay. Okay. All right. Thanks.
Okay. I'm lost now with my, sorry. Okay. Okay, so maybe I just want to show you something on chain complexes. In chain complexes or cochain complexes, we are unbounded. You have this notion of spheres and disk. And the model category structure, I mean, the projective one is a cofibrantly generated model category where the generating cofibration are just embedding of spheres into disk, and the generating a cyclic cofibration are the maps from the initial, from 0 to the disk. Okay, so generating cofibration are so just to recall what is the n, you have r in degree n and r in degree n minus 1. And this has, they represent the functors. I mean, this is precisely representing the evaluation on Cn. Okay, and the sphere represents the cycles of your complex. And when you have a diagram of this sort, it means exactly that. You have an element in B. You have a cycle in A. such that f of A is precisely the boundary of B. And the lift in this diagram says that A is a boundary of something which is sent to B by F. So I would say that what is really important to understand for this chain complex, we are doing homology theory. When we are looking at spectral sequences, we are also doing some homology theory. And what is really important is to understand cycles and boundaries. And the best is indeed to be able to represent cycles and boundaries in some sense by complexes. And for me, it's what makes everything work. So this is the idea of the proof. But the thing is that if you just look at, oops, where I am, sorry. If you just look at usual cycles or maybe boundaries, this is not representable in the nose. So you have to find some trick. So the trick here, and maybe I will be quicker than I wanted for the definition, but when you have a filter complex, I mean, there are many formula. So remember that the R stage of the spectral sequence associated to M is just the R stage of a filtered complex, which is the total complex of M. So there are many formula which explain you that you can express the R stage of the spectral sequence by R cycles modeled by R boundaries. And just to give you an idea of what is an R cycle, so you have a bunch of other elements, sorry, up to R minus 1. No, I forgot the sign, right? This is not really important. So, I mean, this is a formula, and just to be sure that we are okay, it's by graded. So we are by grading PQ, and this is the A0 in PQ, such that you have all this bunch. So maybe just to understand for if M is a bicomplex, you have your A0 here, and you have an A1. So D0 of A0 is sent to 0, and you have an A1 here, such that D1 of A1 is equal to D0 of A0. And you might have an A2 here, such that D1 of A2 equals D0 of A1. And this is an element in the free of M. The problem is that this functor, I mean, it gives a functor from multi-complex to, let's say, R modules, is not representable. So we have to do a trick and we introduce the notion of witness. Sorry, this is a maybe to be sure. So this is witness R cycle. So instead of taking just A0, I'm taking all the elements A0 up to such that star is this. Okay. So proposition, this functor is representable. So in n multicomplexes, so I mean that if I'm fixing n, I have an n multicomplex, which I call, so normally on the screen, this ZW has not exactly the same writing that the ZW, and there's no M. Do you see it, or?
That's good.
That's good, okay. So, and I must put this at PQ, because it's at some point. Here I have again, it's all PQ, A0 is in MPQ. Is an n multicomplex and Hom n multicomplex. So it's what I mean by this. So if n equals 2, so if I'm working with bicomplexes, then ZWR2 is a bicomplexes. If I'm working with multicomplexes, meaning n is infinity, then ZW infinity RPQ is a multicomplex. So for the same functor, I have different representable depending on the place, I mean the n I have chosen. That's the only thing. Maybe I'm trying to, so just to be more clear, what is ZWN0? This is represents MPQ, that's all. ZW1NPQ represents the kernel of M at PQ. Sorry, kernel of the map D0, okay? So just to be sure, maybe I'm too fast, I don't know. Here, ER of M, E0 of M is just M. And E1 of M is just the homology of the complex with respect to D0. So ZW1 is the kernel of D0. So on this, maybe I will go back here to comment this formula. So I have given you the definition of these witness R cycles, and I didn't have explained you this WR and this BWR. So the idea is really that the same as for chain complexes. Look at it, E1 of M, so is the kernel of D0, which is representable, modeled by the image of D0, which is not representable, but WR will be the equivalent of D0 of M. So just M is representable by ZW0, and the map which sends M to the kernel of D0, which is D0, is representable also. It's represented by the inclusion of the sphere into the disk. And in our case, it will work exactly the same. Okay, so maybe I will be just maybe what I call BWR. I'm sorry. And I just again think about chain complexes. A n plus 1 into the cycle and this map D0. Okay, so this BWR will be like something like that, and WR something like the D0. Okay, such that no, so maybe which is represented by a map I'm sorry, just right. And this N multi-complex, BWR, this is just a multi-complex made of copies. So for those people who are used to fitted complexes, this is really natural. So what have we done so far? We have defined what will these elements, maybe I will change colors. Okay. These elements that may like think about disks. I'm sorry, I have a dot or something. And yeah. And this element, I would prefer to think about boundaries. So we will define a set of generating cofibration. So which are these, sorry. Maybe I want to be iota R, which depend on N, which depends on PQ. and PQ is in Z. And some sets, and this is not R, this is R plus 1. So I have a little bit of time, and maybe it's better if I give you example of this ZW. Yeah, I think I will do that, but I just finished now this story about generating cofibration and generating a cyclic cofibration. So maybe I will draw a little bit of a generating cofibration, generating a cyclic cofibration. Oops. So I can take the set in and R here, and here GN0, J, sorry, G and R, J and R. So if I'm taking those two sets, it gives rise to a model category. So think about what are maps that have the right lifting property with respect to Jn0. These are the maps that have the right lifting property with respect to ZW0. But ZW0 is just a n multi-complex that represents the value of your n multi-complex at level PQ. So it just says that if you have the right lifting property with respect to Jn0, it means just that your map is bi-degree-wise surjective. And the right lifting property with respect to J and R says that the map is surjective when you apply the functor ZWR. So this is not exactly the model category structure that I stated in the theorem, but anyway, this is an, let's say, intermediate, or can be useful too. Like you have ER as a set of weak equivalents, and the fibration of the map F, where F surjective, when I write surjective, I just mean bi-degree-wise surjective, and CWRF surjective. So this is one intermediate model category. Now, if you take E and R, and you just add J and K, for K running from 0 to R minus 1, and here you take all the J and K for K lower than R, you get the model structure of the theorem. So just a little bit of check. having the right lifting property with respect to all these maps tells you that not only F is surjective, but also ZW1 of F, ZW2 up to ZWR of F. And this is really equivalent to say that EI of F is surjective for every I lower than R. So do you have any question at this moment? Oops. So maybe I just give you some examples that I have prepared. So I will see if it works, and then I go quickly through this next part. Okay, so this is a bicomplex. So the 2 up there on the W2 is a mean that I have a bicomplex, and it represents the witness R cycle. So the one where, you know, you have A0 such that D0 of A0 is 0. D0 of D1 of A1 is D0, sorry, D0 of A1 is D0 of A0. Sorry. And D1 of A2 is D0 of A1 and so on. So here R equals 3 in this multi-complex. So maybe home of bicomplexes ZW3 to PQ into a bicomplex is this element here, such that D0A0 is 0, D1A0 is D0A1, D1A2 is D0A1. No, sorry, it's not this. D1A1 is D0A2. Another important element is, again, with bicomplexes. So ZW0 represent so this is just represent an element in APQ. So you have this element and you are free in some sense that you don't impose condition on D0 and D1. But because D0 square is 0, this is maybe it's not clear the way I'm writing bicomplexes. A star or a dot mean just a copy of the ring R. And the maps, vertical and horizontal, are just the identity. And if you don't have anything, it means that you have 0. Okay, so you have just a copy of R in PQ, of R in PQ plus 1, P minus 1Q. And P Q, oh, sorry, P minus 1Q plus 1. And a map from this bicomplex to A is just an element in APQ, because the other one will be just D0 of the element, D1 of the element, and then D1, D0, or D0, D1 because they commute. More tricky example is ZW. Oops. Do you see anything? No. This is ZW03. So now it's home of 3 multi-complex. 3. This is much more complicated because D1 square is no more 0. So you have to go through loops. Sorry. I mean, infinitely to the left because D1 square is not 0. You have to generate the relation in some sense that says that D1 square is D0, D2 plus D2, D0. And this gives you the 3 multi-complex generated by one element in bi-degree PQ, which has this form, okay? So of course, writing down all the ZWRN is impossible in some sense. I mean, the combinatorics is really complicated. The good thing is that ZWRN may be obtained as a push-out of ZWR-1 and ZW0. So it's a way we build all the thing. And I mean, if you see the definition of ZWR, I mean, the definition of witness R cycle, they can be defined as pullback. I mean, the functor as pullback, using the functor of at the previous stage. Okay, so what do I mean by comparing model structure? So far what we have the categories of n multi-complexes and n start by 2 up to infinity, and you have R, which is what weak equivalences you are looking at, what you want to localize as what is your homotopy theory you want to look at. So I told you in the beginning that comparing different R is complicated, and in the sense it's, even if we have weak equivalence, R, ER quasi-isomorphism are a subclass of ER plus 1 quasi-isomorphism. But the problem is that for fibration, the subclasses goes the other way around. And so the identity can be left Quillen or right Quillen functor between different R structure. So I mean, we cannot use identity for this. So for filtered complexes, there's so we have also model category structure for filtered complexes with ER quasi-isomorphism. And here you can, in the unbounded case, you can play with Deligne shift and décalage operators that changes your way of seeing the stages of the spectral sequences. And we proved that indeed they are Quillen equivalent in the case of unbounded filtered complexes. But in the case of n multi-complexes, this is much more rigid, and so this cannot happen. However, what we have is that if you have a double complex or I don't remember the other name. Well, a true multi-complex, meaning that you have just D0, D1, and all the others DIs are 0, then of course it's a free multi-complex because D2 is 0, and then so you have all these maps. Okay. So these functors here and so on are right adjoints. So the way to see it is that we have shown that the category of multi-complexes is the same as a category of so vertical bicomplexes, it's just bigraded modules together with a differential D0 of by degree 0, 1. Cn is a ring or a monoid in that category. For n equals 2, C2, it's just dual numbers, okay? So for C3, it's just a quotient. Maybe I can, no, I don't want to explain it. But the consideration of seeing n multi-complexes are modules in the certain category over a ring is that these functors are just a restriction of scalars and extension of scalars with respect to this module, because you have quotient map. I guess that this is the other way around, sorry. Let's see, like this. So what we proved is that for every, maybe it's better to write it, fix r greater than 0, then the categories and of multi-complexes are all Quillen equivalents. So, I mean, for us, this is really important, is that finally, the idea of treating multi-complexes in a homotopy point of view with ER equivalence is equivalent that dealing with just bicomplexes. And well, I guess that this is, we can like strictify at least the multi-complex structure to a bicomplex structure. Now maybe I won't spend too much time on the work in progress because it's something like I'm telling that it's a work in progress till more than more times than needed, I guess. Thing is that what are cofibrant objects? And what is bad in this category is that if I'm putting R, let's say at by degree PQ, and that's all the DIs, just the ring, okay, is not cofibrant. Okay. Even, I mean, this is not a question of having a ring or field or whatever, just not cofibrant. Okay, and I mean, we have a counterexample which proves that it's not cofibrant, but we have a cofibrant resolution. And again, in bicomplexes, I mean, RPQ is a bicomplex because all the DIs are 0. And this is given by I mean, I won't never stop. This is this ladder, and you go to the infinity on the left and on the bottom. Okay. And this is just a projection. So this is a fibration. I mean, this is clearly surjective. And if I'm looking at even the first term of the spectral sequence, I'm taking the homology with respect to D0. I have already my R. So it's an isomorphism at page 1 of the spectral sequence. So just to end, for the present, the only idea that I have I would like a description of cofibrant object like one has for chains or cochains over a ring. And for me, the best description is that for chain and cochain, you have what we call an exact model category structure. I mean, chains are nice enough that you have an additive category. I'm just sorry, I don't know if you hear, but there are gardeners that doing the garden just next to me. So I don't know if it's a problem for you. So this is an exact model category, and a consequence of this is that you can explain cofibration by saying that there are monomorphisms with cofibrant cokernel, and cofibrant objects are described as something projective with respect to some short exact sequence. I won't detail that, but I would love to prove that the category of multi-complexes or bicomplexes, whatever, with this ER quasi-isomorphism is an exact model category structure. And by exact, that I mean, I really need to explain what are the exact sequences in consideration. So I will stop here, and thank you very much for your attention.